Hello and welcome. Today, we're going to take a look at a piece of technology that honestly sounds like it's straight out of science fiction. It's called homomorphic encryption. But don't worry, we're going to skip all the heavy-duty math and really just focus on the intuition. How this stuff actually works and why it's about to completely change the game for data privacy.
And this, right here, is a promise. We're not just going to talk theory. We are literally going to walk you through your very first encrypted computation, step by step. You're going to see for yourself how it's possible to work on data while it stays completely private.
So let's get right into it. What is the fundamental problem we're trying to solve here? Well, it all comes down to trust. We all want to use the incredible power of the cloud for things like data analysis, but we can't just hand over our most sensitive information. Homomorphic encryption acts like a secure bridge. It lets a server, or the cloud, do all that heavy lifting for us without it ever getting a peek at the actual data.
Now, this concept is absolutely crucial. Think of this line down the middle as a hard wall. On the left, you've got your machine. That's the trusted zone. It's where your normal, readable data lives, and most importantly, it's where you keep your secret encryption key. On the right, that's the cloud, the untrusted zone. And here's the golden rule. The key never ever crosses that line. The cloud only ever gets to see scrambled, unreadable data, the ciphertext. This separation is the bedrock of the entire system's security.
Okay, so before we can encrypt anything, we have to lay down some ground rules for our secure little world. This first step is all about configuring what we call the encryption parameters. These are basically the settings that will dictate how everything works from here on out.
Right. And speaking as an engineer, this is where the rubber really meets the road. It's always a balancing act, a trade-off between security and performance. Do you need something that's the digital equivalent of Fort Knox? You can have it, but it's going to be slow. Or can you get by with something a bit more lightweight and faster? Getting these parameters just right is absolutely key to building a system that's actually practical.
So, with our security rules in place, we're ready for the next move. We're going to take our simple, readable data, lock it up tight, and then send it across that security boundary into the cloud.
And to make sure this is super clear, we're going to stick with two of the simplest numbers I can think of, 3 and 5. Look, the numbers themselves don't really matter. What we're focused on here is the process, making sure the encryption and the computation are rock solid.
And here's what that looks like. We take our plain old number 3 and we use our secret key to run it through the encryption process. What comes out the other side is ciphertext. It's just a bunch of what looks like random data with zero obvious connection to the original number. For all the cloud server knows, it's just gibberish. The real value is totally hidden.
Okay, now we get to the really cool part, the bit that honestly feels like a little bit of magic. We're going to ask the cloud server to do math on data that it literally cannot see.
So we send our encrypted 3 and our encrypted 5 over to the server, and we give it instructions. We say, hey, add these two things together and now multiply them. The server just does what it's told. It manipulates that encrypted data, but it has absolutely no idea what the original numbers were. It's doing all of this completely in the dark.
This is what's happening on the server. It gets our two pieces of ciphertext, performs what we call a homomorphic addition, and produces a brand new piece of ciphertext. Now, what the server has no way of knowing is that this new encrypted blob is secretly holding the number 8. It does the same thing for multiplication and ends up with another encrypted blob that's holding the number 15. The server is just a tool, It's just crunching numbers based on our rules. We're the only ones who can actually make sense of the answers.
All right, the cloud's job is done. It did all the heavy lifting for us. Now, it sends those encrypted results back across the security boundary, returning them to our trusted machine for the final reveal.
And here we go, the moment of truth. On the left, you've got the simple math we all know. 3 plus 5 is 8. And on the right, that's the crazy journey our data just went on. We encrypted it, we sent it to a server that couldn't see it, had that server compute on it, got the encrypted result back, and then unlocked it with our secret key. And the final answer, it's 8. A perfect match. It actually works.
So why does adding 3 and 5 in such a complicated way matter so much? Well, because this same exact principle can be scaled up. We're not just talking about adding small numbers. Think bigger. Think about analyzing massive, sensitive data sets, things like medical records or financial data, to find incredible new insights, all without ever putting a single person's privacy at risk.
And that really brings us to the big, forward-looking question. We just proved this works for basic math, but what happens when you apply this same idea to something as complex as machine learning? Just imagine training an AI model on sensitive hospital data to predict diseases.
but with an absolute guarantee that no one, not even the people who built the AI, can ever see an individual patient's file. That is the kind of revolutionary future this technology makes possible.